PBMO is HGL's innovative physics-based management optimization tool, developed to provide optimal solutions of modeled site problems with respect to remedy performance, cleanup time, and costs. PBMO has been applied successfully to environmental remediation and mine dewatering projects by simultaneously optimizing optimal performance and reducing costs. PBMO can be readily customized to develop optimal solutions for multi-objective water resource management projects. The PBMO tool is conceptualized as a medallion with two complementary halves. The bottom half of the medallion consists of a site-specific, calibrated physics-based flow and transport model. The top half consists of the PBMO Computational Optimizer module, containing a suite of optimization algorithms used to identify optimal solutions to complex flow and transport problems. Existing industry-standard graphic user interfaces, or GUIs, are used to facilitate input preparation for the physics-based simulators. An optimization user interface, or OUI, is used to define and facilitate the input preparation for the optimizer incorporating stakeholder requirements. PBMO then uses input from the OUI to develop and dispatch batches of scenario-specific simulations. PBMO assesses system performance and continues the search until an optimal solution is obtained. As batches of scenarios are running, PBMO provides visual representations of results using an optimization dashboard for transparency that can be shared with all project stakeholders. The PBMO Optimizer module resides in the upper half of the medallion. This cutting-edge optimizer contains a complete assemblage of computational optimization algorithms for conducting a systematic search of global maximum and minimum values, or peaks and valleys, of the multimodal objective functions for the given optimization problem. Key elements of the computational optimization include objective functions, the value you want to optimize, such as minimizing cost or time to remediation; variables, aspects of the problem that can be varied, such as pumping rates and locations; and constraints, aspects of the problem that cannot be changed, such as treatment system capacity or compliance boundaries. PBMO uses a select group of computation optimization algorithms. These algorithms and their functionality are described in the PBMO code documentation and in the management science literature. Presently, the lower half of the PBMO medallion contains ModFlow-based groundwater flow and contaminant transport simulation codes, including public domain ModFlow and MT3 DMS, and HGL's state-of-the-art ModFlow Surfact code. Notably, PBMO can readily be customized to accept other groundwater codes and codes for surface water and integrated surface groundwater modeling, including HEC-RAS, HEC-HMS, and MOD-HMS. The PBMO technology is deployed on a cloud computing platform. With parallel processing in the cloud, complex optimization problems can be solved within a reasonable time frame. To use PBMO in the cloud environment, a user, sitting at a terminal, uploads a calibrated flow and transport model to the secure cloud location where the physics-based model and optimization algorithms within PBMO reside. PBMO takes input from the OUI and distributes scenarios to the central processing units, or CPUs, in the cloud environment. PBMO then assesses each scenario relative to the stated objectives and redistributes additional scenarios as needed until the optimal scenario is achieved. Results for feasible solutions are returned in batches of scenarios to the user and can be viewed via the objective function graph, which plots objective function versus model scenario number. As subsequent batches of model scenarios are plotted, the objective function exhibits a downward trend and eventually converges on the optimal solution. Notice there could also be humps at the beginning of each batch, as PBMO assesses new decision space for each batch. For each scenario, the OUI plots the objective function graph, as well as other results, showing scenario-specific remedy performance, remedy costs, and value of decision variables within a concise project dashboard. 5 demonstration examples are provided and available for viewing to document successful application of PBMO to problems with various requirements and complexities. These examples include the following: benchmark problem, Umatilla Army Depot, Umatilla, Oregon. A pump and treat remedy design optimization for adjacent RDX and TNT plumes. Superfund site. Complex pump and treat remedy design implementation optimization involving over 4,500 decision variables and large carbon tetrachloride plume, as well as a nearby off-site TNT plume. The BRAC Army Site. Optimization exit strategy for performance-based remediation project involving large, diffuse TCE plume. FUD's Army Installation. A pump-and-treat remedy optimization for large RDX plume. Open pit mine, Western Australia. An optimization of dewatering and excavation strategy over 2 decades. This application requires variably saturated flow simulations.